In today's video, we are going to be talking about how to solve absolute value inequalities. This is very similar to absolute value equations, but we do have a couple more steps that we need to follow when it comes to solving, as well as when it comes to showing our answer. The first thing that I want to talk about is the two options we have when it comes to graphing. We may have great or than or less than. If something has a greater than symbol, it's going to have two different categories where it's one or the other, and they'll go in two different directions. If we have a problem with a less than sign, we have two answers that are actually going to go together, and we call this less than because it has to be bigger than one number and less than another number to fall in between those two places. This is going to sort of kind of tie a lot of the things that we've done together in this unit by bringing up open and closed points when graphing, solving equations, as well as absolute value. We're going to go ahead and start with problem number 1. So just like we did in our previous absolute value notes, is step 1 is to get the absolute value marks alone. As we see here, the absolute value marks are already by themselves. I have the absolute value marks, and then everything else is on the other side. Since I don't have to worry about step 1, I'm going to move on to step 2. Set up two cases. So anytime we solve an absolute value equation or inequality, we're always going to have two cases that we need to solve. My first case is always going to look exactly like the equation or inequality I had originally. It's just going to drop the absolute value bars. So I would have 2x minus 3 is greater than or equal to 7. Case number 2 is going to have the same first part. So the 2x minus 3 doesn't change. But whenever I find my second case for an absolute value inequality, not only do I have to change that number to a negative, but I also need to flip my inequality sign. And the reason that we do that is because we're flipping the direction that we were moving on the number line. If something is bigger than 7 spaces away, it would have to be a number that's smaller than negative 7. So anytime we set up our two cases, we always flip the inequality and make it negative in the second case. From there, my step 3 is to solve for x. So to solve for x, I'm going to add 3 to each side. And that leaves me with 2x is greater than or equal to 10. And 2x is less than or equal to negative 4. After that, I need to divide each side by 2. That gives me x is greater than or equal to 5. And x is less than or equal to negative 2. Now, it doesn't ask us to just solve it. It asks us to graph. So my final step is to graph. To be able to do my graph, I need to draw a number line and label it with my two solutions that I found. We want to put these from lowest to highest. So I have negative 2 and 5 labeled on my graph. In order to find out if we're dealing with a great or than or less than graph, I need to look at what the inequality sign was whenever I split it up into cases. So I want to look at the inequality sign that I see in that first case to know which direction I need to go in. Because my first case is great or than, that means that I'm going to be coloring the edges away from each other. So I would want to shade away from -2 and away from +5. A good way to check your answer is we want x values that are greater than or equal to 5, which falls up here, and we want x values that are less than or equal to -2. There are no numbers in the world that are bigger than 5 and less than -2, so we have to color the edges because there's not going to be any overlap. We're going to work through number 2 as well. When I get to number 2, my step 1 is to get my absolute value marks alone. Looking at my problem, I have the absolute value marks on one side and everything else on the other. So that means I'm going to go ahead and set up my 2 cases. My first case looks exactly like my equation. I just drop my inequality. I just drop the absolute value marks. My second case, the 2x minus 4 stays the same, but I have to flip my inequality sign and change it to a negative number. Technically, we flip the sign whenever we solve an absolute value in an equation. We just don't know it because an equals mark looks the same forwards as backwards. Once I have my 2 cases set up, I'm going to go ahead and solve each equation. So I added 4 to each side, which gives me 2x is less than 10. And to get the x by itself, I'm going to divide by 2. So x is less than 5. I'm going to follow those same steps to solve on my second case. Once I get here, I see x is less than 5, and I see x is greater than -1. These are my 2 solutions, so I need to figure out a way to show them on a graph. My first value is -1, and my last value is +5. I want x values that are less than 5 and x values that are greater than -1. Because my sign right here is a less than sign, that means that I'm going to be coloring in between these 2 points. Since it's just a less than and a greater than sign, I'm going to use an open circle for each one of these. Whenever you take a quiz or a test with these, always double check to make sure if you're using open points or closed points. That's one place where they like to trip you guys up a little bit. And when I go back and look at my restrictions, these x's are less than 5, but they're also greater than -1. So they meet both categories, which is why we have the and. We're going to move on down to talk about some special cases really quick. As we look at special cases, one thing I want you guys to remember is when we did our absolute value equations, things always got a little tricky whenever we had a negative sign pop up. We always want to be cautious and see what may happen or any tricks that may occur because of a negative. If the absolute value is greater than or equal or greater than or equal to a negative number, it will always be all reals. So an absolute value greater or greater than or equal to a negative number will always be all reals. An absolute value less than or equal to a negative number will always be no solution. We're going to look at each of these examples to figure out which case is which. As I look at number 3, I see I have the absolute value bars, but they aren't by themselves. To get the absolute value marks by themselves, I'm going to have to subtract 5 from each side. And that gives me the absolute value of 2/3 x plus 4 is less than or equal to a -6. Anytime you see a problem like this, you have a flashing red light going off in your head telling you warning, warning, danger, danger, because there's a negative sign. One thing that we know about an absolute value is absolute value is always positive. So is a positive number ever going to be smaller than a negative number? No. This is going to be no solution because there is never a time where a positive number is going to be less than or equal to a negative number. This falls in with my second category. For example number 4, the thing that I notice here is that there is a -2 out front. Because I don't have a plus or minus sign in between the 2 and the absolute value mark, that means I'm going to need to divide each side by -2. And I'm going to put a little flashing warning sign. When you divide by a negative, the inequality sign must flip. So because I divided by a -2, that means that I am going to have to flip the inequality sign. So when I divide by -2, my 2's cancel out, and I'm left with the absolute value of x minus 3 is greater than -4. Now, once we notice that this has a negative number attached to it, we're going to stop and figure out if this is all reals or no solution. Is a positive number going to always be bigger than a negative number? Yes, a positive, no matter what that positive number may be, is always going to be bigger than a negative. So this would be all reals. The final thing that we're going to cover in this notes video is a couple of word problems. These word problems are referred to as tolerance word problems. They help you sort of kind of like the margin of error problem that we talked about in absolute value equations. They help you to see how much of a difference you can tolerate between what you actually receive and what you would ideally receive. A good example of this is if you buy a bottle of Cheerwine out of a vending machine. You would tolerate a little bit of the drink being empty because, hey, maybe they underfilled it a little bit in case it spewed when you opened it. But you wouldn't tolerate half of the bottle being gone. That's why we call these tolerance word problems. They will always follow the formula, the absolute value of actual minus ideal is less than or equal to the tolerance. So we're going to work through a couple problems like that. A carpenter is using a tool to shape the final leg of a handcrafted table. In order for the leg to fit, it needs to be 150 millimeters wide. Allowing for a margin of error of 2.5 millimeters, write an absolute value inequality that models this relationship, and then find the range of widths that the table leg can be. Before we go any further, I want to point out that tolerance is the same as margin of error. They mean the exact same thing. So we don't know what the actual size of the table leg is because it's handcrafted and we need to make the leg to fit the table. So I'm going to put an X in for the actual value. The ideal value is 150, and our margin of error, or our tolerance, is 2.5. Anything above 2.5 off will not work. This is the absolute value inequality that models the relationship. Now we need to find the range of widths that the table leg can be. To do that, we're going to have to split our absolute value equation into two different cases. So the absolute value of x minus 150 is less than or equal to 2.5. As we split that up into two cases, I have x minus 150 is less than or equal to 2.5, and x minus 150 is greater than or equal to negative 2.5. To solve my equation, I'm going to add 150 to each side. When I do that, I end up with x is less than or equal to 152.5, or x is greater than or equal to 147.5. It asks the range of the widths that the table leg can be. So the table leg can be anywhere from 147.5 to 152.5 millimeters. This is where these absolute value equations and inequalities come into play. A lot of times we may be using these for the margin of error if we're creating something on our own. Or we may use tolerance problems like this to help us plug in a formula into a machine or something like that in a factory so that it can do a job for us and make sure that it's meeting the standard set. We're going to go through example 6 and we will be done with our notes for this unit. Example 6. A manufacturer allows a maximum of 18.5 ounces of cereal and a minimum of 16.25 ounces of cereal per box. Write an absolute value inequality that demonstrates the manufacturer's constraint. So the information that I was told here is that my minimum is 16.25 and my max is 18.5. While this doesn't tell us an ideal or a tolerance or even an actual, there's a way that we can find out what our ideal is. Our ideal is equal to the minimum plus the maximum divided by 2. So to find out what our ideal is for this box of cereal, whatever would be listed on the packaging, we're going to put our minimum plus our maximum and divide it by 2. And that is going to give me, sorry you guys, I'm doing the math in my head. Let me just type it in a calculator like you guys would. I'm going to type it into my calculator. Sorry about the lighting again. 16.25 plus 18.5 divided by 2. That would be 17.375. This value is our actual, or is our ideal. We don't know what the actual box is. The actual box depends on which box you pick up. So we now know x minus 17.375. But we still don't know what our tolerance or our margin of error is. To find our tolerance, we have to do our max, or we could do our minimum, minus the ideal. So we have to find out how far it is from the ideal to the maximum. Whenever I do this, I end up with 1.125. So my margin of error, or my tolerance for this problem, is 1.125. And that is the absolute value inequality that represents the manufacturer's constraints. The reason that we would need to find something like that is if we were programming a set formula into a factory at a machine that distributes the cereal. So this is a place where math comes into real life. It helps with carpentry. It helps with manufacturing. So let me know if you guys have any questions about absolute value inequalities. I'm always here to support you guys and answer any questions that you may have.